Every machinery part has its own specific geometry and manufacturing requirements. Some have complex geometry, with tight tolerances that require specialized knowledge and equipment to reverse engineer. Gears are ubiquitous pieces of equipment with very specific shapes. The geometry of gears in modern machinery conform to various standards that allow interchangeability and maximized efficiency. However, there are still a large number of different gear types, some with very similar geometry, which means many criteria have to be examined in order to fully identify a gear's specifications. We successfully reverse engineer a wide variety of common and uncommon gear types, including straight bevel, spiral bevel, spur, and helical gears. For most gears, we can quickly and accurately measure gear features with handheld tools. Once measurements have been taken, we utilize specialized software to verify what standard the gear conforms to. For gears with more advanced geometry, such as helix gears, we employ our more advanced metrology equipment, like the Faro Touch Probe Arm, in order to determine pitch angle and other specifications. For truly unique and non-standard gears, we make use of an M&M analytical gear inspection machine. When all the necessary information is collected, we can generate a CAD model of any gear with precise teeth geometry, ready for manufacturing. While similar in appearance to gears, splines transmit rotary motion along a single axis. Splines also have less versatile roles than gears, which means they are less varied and therefore easier to identify. Our large collection of spline gauges allows us to quickly verify the identity of a spline with few measurements. More challenging to reverse engineer than gears or splines are cams. Like gears, cams come in a variety of designs such as barrel, open-ended barrel, or ring cams. However, unlike gears, there is no standard geometry for a cam. A cam functions as a guide for a roller. The shape of the cam is dependent on whatever unique set of motions the roller is intended to go through. Precise roller movement requires tight tolerances on the cam surface, and the shape must be mathematically tailored for proper accelerations. In order to accurately capture this critical geometry, we collect displacement values on the roller, paired with angle of rotation values on the cam. Plotting the displacement with the angle allows us to build a profile of the cam. The profile can then be tailored based on mathematical principles to ensure it performs as intended. Finally, a drawing and solid model can be created for the cam, readying it for manufacture.